Today, we are going to crack the code on a subject that, let's be honest, terrifies a lot of students: organic chemistry. But I'm going to let you in on a little secret. It's not about memorizing a million different things. It's actually about learning a language that has its own alphabet, its own grammar, its own rules. And once you get those down, you can understand pretty much any reaction they throw at you. So if you've ever sat there staring at a textbook, feeling totally and completely overwhelmed by this stuff, you are definitely not alone. I remember my own experience so clearly. Sitting in this huge exam hall, my heart is just pounding, and this cold wave of panic just washes over me. Yep, that was me, staring at a page full of these complex molecules, and it felt like it was written in a completely alien language. But you know what? That feeling of being totally lost, that's exactly why we're doing this. We're going to break that code together, piece by piece. So here's our game plan. We're going to use what I call a building blocks approach. First, we'll learn the alphabet of chemistry, these special groups that just pop up everywhere. Then, we'll figure out the word structure, why their position is so important. After that, we'll dive into the grammar of reactions, meet the attackers that make things happen, and finally, put all these building blocks together to understand the whole chemical story. Okay, so let's just reset how we think about this. This isn't just another science class. Think of it more like a language course. And with any language, you don't start by memorizing the entire dictionary, right? No, you start with the absolute basics. The real secret here is that there are just a handful of core concepts that act like the letters of an alphabet. If you can master these, you'll be able to read and even predict how molecules behave. This is the key that unlocks everything. So let's start with our very first letters. All right, our first set of letters are these special groups. These are common combinations of atoms you're going to see over and over again. And I'm going to show you a really simple trick to remember their names and structures, just by looking at the word itself. This is where that language analogy gets really, really cool. We're going to borrow a concept from linguistics called sandhi bitshed, which basically just means word splitting. So for example, take the name enol. If we split it, we get N, which in chemistry is the code for a double bond, and ol, which is the code for an alcohol. You put them together, and what do you have? An enol is just a molecule that has both a double bond and an alcohol group. See? The name literally tells you the structure. And this trick works for other groups too. Check out amine. You split it, N plus amine. So that means you've got a double bond somewhere and a separate amine group somewhere else. But now look at imine. Here, the double bond is directly on the nitrogen atom itself. It's a small change in the name, but it leads to a totally different structure. That's the power of thinking this way. And this same logic of combining parts applies to a bunch of other key groups you're going to run into. A lactam, well, that's just an amide that's been folded into a ring. An epoxy, that's a tiny, super reactive ring with an oxygen in it. And notice the pattern with hemiacetals and acetals. Hemi means half, right? So a hemiacetal has one alcohol and one ether on the same carbon. A full acetal has two ethers. It's all about just recognizing these patterns. Okay, so we have our letters. Now let's talk about word structure. In chemistry, it's not enough to just know what groups are there. You have to know where they are. Their position is everything. And that's where this concept of degrees comes into play. To understand degrees, you first have to find the alpha carbon. This is the carbon atom that's sitting right next to your main functional group, like an alcohol. It's really the center of the action. Now here's a super common mistake. People pick the carbon that's inside the functional group. Don't do that. It's always the one attached to it. So once you've found that alpha carbon, figuring out its degree is actually pretty easy. You just count how many other carbon atoms are directly connected to it. If there's one, it's a primary, or 1-degree carbon. 2 connections, it's secondary, 2 degrees. 3, it's tertiary, or 3 degrees. And trust me, this number is so important because it completely changes how that molecule is going to react. All right, so we've got our alphabet and our word structure. Now it's time for the grammar, the rules that tell us how molecules actually interact with each other. How do they change? Well, it all comes down to one single fundamental process. And that's it. That's really the entire story of chemistry in one sentence. Every single complex, crazy, multi-step reaction you'll ever see is just a sequence of these two simple events. An old bond breaks and a new bond forms. So let's look at how they break. So a bond is basically just 2 shared electrons, and it can break in one of 2 ways. In a homolytic split, it breaks nice and symmetrically. Each atom gets 1 electron back, And you end up with these really reactive things called free radicals. But in a heterolytic split, it's totally asymmetric. One atom is greedy and takes both electrons, becoming negatively charged. The other one is left with nothing, becoming positively charged. When this happens to a carbon, we get a positive carbocation or a negative carbanion. So why does any of this matter? Well, it all comes down to stability. Think of those carbon groups we counted earlier as supportive friends. Free radicals and carbocations are kind of needy. They're electron deficient. So being surrounded by more supportive carbon friends, being tertiary or 3 degree, makes them way more stable. But carbanions are the exact opposite. They're electron rich. They're kind of overwhelmed. So more friends just adds to the crowding and makes them less stable. That's why for carbanions, the trend is completely flipped on its head. So we know that bonds break, and they create these unstable intermediates. But what starts that whole process? What actually initiates the break? That's where our next set of characters comes in. The attackers, which we call reagents. In pretty much any reaction, you've got the main molecule that's being worked on. We call that the substrate. And then you have the attacker, the reagent. It's usually the smaller, more aggressive molecule that just comes in and kicks off the whole chain of events. Now, reagents come in two main flavors. First, you've got the electrophiles, or electron lovers. And just like the name says, they are electron deficient, and they are constantly on the hunt for electrons. This could be anything with a positive charge, or even neutral molecules that just don't have a full set of electrons. And because they accept electron pairs, we also call them Lewis acids. And on the other side of the coin, you have the nucleophiles, or nucleus lovers. These guys have an excess of electrons, either a negative charge or spare lone pairs, and they are looking to donate them to something positive. Because they're electron pair donors, they are your classic Lewis bases. Okay, let's step back for a second and just look at what we've assembled here. We've got our alphabet of functional groups. We have the structural rules of position and degree. We've got the grammar for how bonds break, and we have our main characters, the electrophiles and nucleophiles that drive the whole story. This is it. This is your fundamental toolkit. And with it, organic chemistry stops being this terrifying list of things to memorize and starts becoming a puzzle that you can actually solve. Now you can look at any reaction, identify the key players, assess the stability, and figure out who's attacking who. You actually have the tools to predict what's going to happen, even if you've never seen that exact reaction before. You know, the source material that inspired this had this really interesting thought that I want to share. This whole principle doesn't just apply to molecules. Life is also this constant cycle of breaking old bonds and forming new ones. Every plan that falls apart, every failure, it isn't really an end. It's just the breaking of one bond, clearing the path for a new, maybe even stronger one to form. So I'm going to leave you with this question. We've seen that chemistry is this incredibly dynamic science of transformation. It's all about breaking down what's old to build something new. So now that you have this knowledge, what are you going to build? What new connections are you going to make?